Hello everyone, welcome to my channel. This is Xiaofu. Currently, I'm a staff control engineer working at ASML. On the side, I'm also doing my own startup company. So in this series of videos, I'm going to share my knowledge on control system and related algorithms design. So in this series of video, I'm going to continue to teach you how you can design a control system from scratch. So this is a summary of this lecture. First of all, we are going to introduce the concept of transfer function and also state space model. Then later on, we are going to discuss what is LTI system and showcase some examples. At the very last, we are going to derive a transfer function of a quarter car model. This is just part 1. So in lecture 3, we are going to have part 2. Derive the transfer function of a quarter car model entirely and demonstrate with MATLAB simulation. After that, we are going to derive space model of a quarter car system. So if you like my video, please subscribe to my video. Thank you. So as we all know, so a control system, simply speaking, is a control input applied to a plant model. And that plant model will behave accordingly based on its own system dynamics. And then you have a output Y, which can be measured by sensor. It can be displacement, velocity, temperature, pressure, and using those feedback information, you compare with your reference and you correct it based on the error. So generally, the plant can be modeled by higher order differential equations. And if you try to represent that with state space model, which we are going to discuss more in the next video, but that one you will have to translate from higher order differential equation that you derive from equation of motion or Newton's second law, and then translate into multiple first order differential equation, which can be used to represent your state space representation. And on top of that, so transfer function, in this series of lectures, we are focusing on LTI, which means linear time invariant system. So transfer function is a Laplace domain, or in a sense, frequency domain, assuming initial condition 0, which is a ratio of output versus input. So as I just mentioned, right, so we have different system representations, right? So ordinary differential equations, in control system, there wasn't a real advantage. Well, these ordinary differential equations will be a prerequisite or the basis fundamentals that you can use to derive your state space model. And advantage of transfer function, as I just mentioned, it is in frequency domain. It is great for dealing with interconnected systems. The advantage, of course, becomes less pronounced, however, for multi-input and multi-output systems. So I would say large or only large disadvantage will be only applicable to linear time invariant system. For nonlinear system, you might need a linearization or different approach if you really want to apply transfer function. State space representations easy to drive for higher order and MIMO systems, but can also lead to relatively straightforward control design framework that is applicable to higher order and MIMO systems. Well, regarding the disadvantage of a state space model, it is difficult to analyze interconnected system based on state space representations, but for isolated one, it's much easier. Okay, so for LTI system, the first term that we mentioned is linear, right? Linearity, given a system described by ODEs, ordinary differential equations, the linearity generally have two properties. One is scaling or in the word, another word is homogeneous, right? The other one is superposition, which is additivity. So as you can see, the following system is linear, and if and only if it meets those two properties. So g of t, g is a function of time, u which is a input, y you can consider this as an output, right? So to check for linearity, we make sure that the time t appears as a coefficient, not just a standalone term. Another one for output and input and all derivatives thereof also appear linearly. The third one is make sure there is no standalone constants. Otherwise, will be considered as nonlinear system or not following LTI prerequisite. So we are going to use a couple of examples here. Let's assume y, which means function f of y. If you go back to the previous slide, your function f of y is equals to y, and your function g of u equals to 5u. And simply just using these, let's say, standards to determine, we see that it meets linearity property. So this should be a linear system. Well, we can use actual numbers to give it a try. So in this example, let's assume we have a, b, and plug into this equation f of ay1 plus b of by2 equals to ay1 plus by2, and let's say whether it meets the scaling or homogeneous property. So it is supposed to equals to a times fy1 plus b times fy2, right? So we compare them; those two are equal. And let's check the function g of u. G of au1 plus bu2 on the left hand side equals to a g of u1 plus g of u2 for all the a, b, u1, u2, right? So this, of course, very obviously, this is meeting the standard to be considered as linear. And let's use another example, which is nonlinear system. Your y equals to u squared, right? This time we use actual numbers to try it out. Let's assume a equals to 3, b equals to 0, u1 equals to 4, u2 equals to 0 again. G of au1 plus bu2 is g of 12, right? And then g12, if you plug into this equation, u squared, g12 equals to 12 squared, which is 144. And if we use AGU1, here let's say your U1 equals to 4. GU1 means 4 squared, which is 16. A equals to 3. 3 times 16 equals to 48. And BU2, as B is 0, multiplied by anything, it should be 0 again. So you get 48 not equals to 144. So this is nonlinear. And the last one is, okay, as you can see, this function g of u is consisting of a standalone constant, right? So which means this is not linear. But we still use an example to prove. Let's assume a equals to 2, u1 equals to 4, b equals to 0, u2 equals to 0. The reason why we would like to use 0 here because it's as easy for us to quickly prove this example. Let's say g of au1 plus bu2 equals to, let's b equal to 0, we don't consider bu2, a times u1, which is 8, g8, right? If you plug 8 back to the equation, that's g of u equals to u plus 7. This equals to 15, right? And then if you separate it out, write it as a times gu1 plus b times gu2. As b equals to 0, we only consider a times gu1. u1 equals to 4. gu1 equals to 4 plus 7, which is 11. 11 times 2, which is 22. these obviously are not equal. Well, if you really want to make a different representation, consider this as a linear system. You might can write u plus 7 as delta u, and then y equals to delta u becomes a linear system. So there will be a lot of different tricks over there that you can convert nonlinear system into linear system, right? Okay, so another important system property will be time invariance, right? So we mentioned we are dealing with linear time invariant system, LTI system. So the differential equation describing the system doesn't depend explicitly on time. So that means not explicitly dependence on time. So you can write your function f as y, g as u. So you probably can also have first, second, or higher order derivatives over there, but they don't explicitly depend on t. But why those are important and useful, LTI system, is because the free response of LTI system is comprised entirely of exponentials, sines, and cosines. Easy to predict. And for LTI system, important properties like stability, time constants, oscillation frequency, steady state gain can be established. So time constant can be considered how quickly it die out the transient response. And oscillation frequency is a separate topic. But those are all combining together to give us this LTI system characteristics. So after we have done examples, so here we have some other examples to be shown so that we can consider whether those are linear or nonlinear system. So first one, as we mentioned, g of y, so f of y, g of u, as you can see, f of y is a function of y and y dot. And g of u is a function of u, right? So it's a linear time invariant system. The second one, we have y squared and a standalone constant, so that's nonlinear time invariant system. So the third one is nonlinear because you have the standalone constant. The last one, though there was no standalone constant, but the time t comes out as a standalone term, so it's no longer explicitly depend on t. So it still become a nonlinear time invariant system. So the last one, we have t, but is part of a coefficient, right? It's considered as a coefficient. Then it will still a LTI. It will still a linear system, but not time invariant because you have a t explicitly shows up. So it's a linear time variant system. So the previous one, as I mentioned, so 5t, even though it's not, even though you are standalone, but you also have a t explicitly in your system, so it's also time variant, not time invariant. Okay, so the coming topic that we are going to discuss, which is deriving the transfer function by using a quarter car model, right? If you don't have vehicle dynamics background, you might just can quickly search ChatGPT or Google what are quarter car model system, right? So quarter car model system, you have sprung mass and sprung mass. So the n sprung mass, you can simply consider this is the mass under the suspension system. The unsprung means unsuspended system. So this unsuspended system is basically can be simply considered as the tire. And if you consider the tire system, so you have the tire mass, and tire can also itself considered as a spring and damper system altogether. But of course, this mass not only have tire itself, also have the tire rim, also have the chassis and any other components associated with it. So Z0 here is the road input going directly to the tire. For the sprung mass, which can be considered supported by the suspension system. So suspension system, you probably can have, let's say, passengers, your engines, anything else that you can think of that can be supported by the suspension system, right? So your direct actual very initial input is from the road condition, right? Different road condition, you have a disturbance or input to your system, right? Your system is this quarter car model, including this suspension, tire, and everything else. So your actual output is Z of S. So ZS can be considered as a metric to evaluate the comfortness of the passenger. So right now we are going to derive the equation of motion by using Newton's second law, and from equation of motion we are going to translate our ordinary differential equations into Laplace domain. So this quarter car model, if we split it out into sprung and unsprung mass, so let's start from the very top. The sprung mass will be subjected to this spring mass and damper force, and all of them all together. Of course, you also have your gravity force, which is mass times gravity, right? So those three. Unsprung mass is the one in the middle. So other than using Newton's second law, also apply Newton's third law, right? Action-reaction force. So you have action-reaction force also from sprung mass that is applied here, which is the same magnitude, opposite direction. So another one is it is coming from the bottom spring mass system itself, KT and CT, right? So free body diagram is simple and also straightforward. So let's use Newton's second law to write down sprung and unsprung mass, their equation of motion. So the swing mass, you have to consider the relative displacement in between, right? Between sprung mass and unsprung mass, your, let's say, relatively moving displacement is Z of S subtract by Z of US or mu S. So similarly, your damping force is considered also as the derivative of the displacement. So you just take the derivative of the delta x, so you get Z of S dot minus by Z of US dot. So this is the sprung mass dynamics. And then for unsprung mass, we follow the same approach, right? So you have the force applied by the sprung mass, which is Fks plus Fcs, right? Then you also have the force applied by the bottom spring and also damping. And also the last one, you also have the mass itself have the gravity force. So following the same approach, as the damping is always proportional to the first order derivative of the displacement, namely it is proportional to the velocity. So applying the same thing, you get the following equation of motion. So let's just simplify the equation of motion. Let's write it down all together. Let's say we have sprung mass, which we derive from the previous equation. We also have the unsprung mass that is listed on the second one. So from time domain to Laplace domain, if you apply Laplace transform, you are going to also a similar domain to frequency domain. So as we consider zero initial conditions, so that means your second derivative can be considered as s, which is Laplace variable s squared times z of s. I'm using the sprung mass equation as an example to explain. right? Since you have initial condition as zero initial condition. So simply z u of s, zs, there's no first order or second order derivative, so you don't have this s term multiplied by it. But for first order, you can consider first order, you have s to the power 1. Second order is s to the power 2. So then you get the Laplace transform domain. For the, let's say, then after the sprung S, for the unsprung S, you do the same thing, right? You do the same thing. First order, you have s to the power times the variable in S domain itself, right? Second order, you have the s to the power 2 times the variable itself in S domain. So following this format, you get all the Laplace transform. So S, from our transfer function perspective, our initial input is z0, right, from the road, and our final output is z of s, which is the metric we use to evaluate the passenger comfortness, right? So as of now, if you check your let's say your sprung mass, you have this equation of motion, and you translate it into Laplace domain. You move everything, have z of us in one side and z of s on the other side. So you get this following Laplace domain function. So you move everything in one side and combine them and get the ratio. So that's how you get the z unsprung mass of s equals to a function of z s of s, right? So right now, since we need a relation between z0s to the z s of s, right? So right now, still we are halfway done. So in the next slide or in the next lecture, I'm going to show you the rest of the derivation, how you derive this z0s to zss transfer function. Thank you all for listening. If you like my video, please subscribe to my channel. That will give me a lot of motivation to keep making more videos. Thank you.